Hello everyone, welcome to section 9.3 of chapter 9 and nuclear radiation. And so in section 9.3 we're going to look at how we measure radiation, whether it is like naturally occurring radiation like we're seeing in this picture, or when we're measuring it because we're using it or we have to work around it so we can make sure that we're protecting ourselves adequately. So you've probably heard of a Geiger counter, and a Geiger counter is a instrument that detects beta and gamma rays. We're not so worried about alphas. It uses ions produced by the radiation, and it produces an electrical current that is a flow of electrons, and then that allows us to pick up the radiation and convert that into a number so that we can figure out what that is. And you always will have, just like with most instruments, you're going to have some standardized radioactive source where you can make sure that it's reading correctly. So there are units for measuring radiation. There is the Curie, and if you recall me talking about Marie Curie, it's named after her. It measures the activity as the number of atoms that decay in 1 second. How many atoms decay in 1 second? So what we're doing is we're measuring activity. Okay, a rad, which is a radiation absorbed dose, measures radiation absorbed by the tissues of the body, and a rem, which is radiation equivalent, measures the biological damage caused by those types of radiation. So Curie is activity, rad is the radiation that you would absorb from a certain source, and the rem is how much it would hurt you and damage your tissue. So as you can see here, the Curie is commonly what we use, and the becquerel is another unit that you may see as well. There are 3.7 times 10 to the 10 becquerels in 1 Curie if you need that in a conversion. The absorbed dose of a rad, the SI unit for that is a gray, and a gray is 100 rads. And then the rem is you have to have a particular factor depending on what the material is to get a sievert, okay, and 1 sievert is around 100 rems. And so often the equivalent dose, though, because we don't want much gamma, is in millirems, okay, because that's 1,000 millirems in a rem, and so we're looking at very small quantities usually because we're very susceptible to these gamma rays, and so we want to make sure we keep that dosage as low as possible. We can get exposure from different places. We've already seen that we have naturally occurring radioisotopes in nature. Dental and medical procedures where we get x-rays. Whenever you go high in elevation, like in a very high mountainous area, or even flying in an airplane, you get high enough to where you're not as protected by the atmosphere, and so you can get more radiation. And if you take off in a rocket ship and go all the way out of our atmosphere, then there is great concern for accumulating too much radiation. Radon gas is a concern. A lot of people, if you have rocky or clay areas, you can actually be exposed to that if your house is too well insulated and hooked up tight. You can actually accumulate radon gas, which is a nuclear radiation. Smoking cigarettes can actually, one more thing that cigarettes do that you don't want. Cigarettes can actually have some natural occurring radiation in them. And then, of course, as I said, the cosmic rays, if you happen to make it to outer space or whatever, you could get some of those exposures to them. We don't get so much down here, only about 40 millirems, so not too bad. Some of your, and most of your medical exposures are pretty low. They're close to background, okay? But radon can be pretty high, so You got to really kind of watch that. And some types of x-rays can also dose you pretty good too, so that's why they don't do those unless they just absolutely have to. So if you get sick with radiation, which isn't going to occur with most of us, although anytime we do a nuclear test or someone does a nuclear test, in theory it's going to increase the background radiation content. If there were ever a nuclear war or whatever, then it would increase the background dosage, and we're not sure exactly what it would do to life, but because it does cause mutations. But the LD50 is the amount of radiation that the whole body, that's the lethal dose for half the population, or 50%. That's where that 50 comes from. So the lethal dose at 50%, and it depends on what you are, what type of organism you are, as to what your LD50 is. Insects, notice, that's why they've been around for a gazillion years, is because they can take a lot of REMs. Bacteria can also be very stable with radioactivity, some of them. Rats do better than we do at 800 REMs. We're at 500, and our little puppies would not make it. They would die before we did. So it doesn't take many REMs to kill off half of us, and the rest of us would probably be like some of those mutant movies that you see on TV. All right, let's just work a quick problem and with some of these. This is a typical thing that you might see, a typical intravenous dose of iodine 125. Iodine is used for thyroids because the iodine collects in the thyroid. That's your thyroid hormones, all have iodine in them. And so the diagnostic test that's using 100 microcuries, that's 10 to the minus 6 curies, and it wants to know what's the dosage in megabecquerels, and that gives you that 3.7 times 10 to the 10 becquerels equals 1 curie. So put me on hold, look up some of those conversion factors, try to work this, and then come back. All right, so I'm going to work it my way. You can do that desired and all that that they do in medicine, but the chemistry way, if you recall, is that you start with what you have. So you have 100 microcuries, and we know that 1 micro anything is what? I told you, 1 times 10 to the 6 No, wait, did I mess that up? I did, didn't I? Alright, I think I still have an eraser. Well, I'm just going to mark it off. Alright, ignore that. Alright, microcuries, I didn't do my own rule, right? Microcuries. I know that's smaller, so that's 1 times 10 to the 6 for every 1 curie. Okay? That way I can get rid of that. All right, I know that there are 3.7 times 10 to the 10 becquerels in 1 curie, so 1 curie goes down here, and 3.7 times 10 to the 10 becquerels goes there, and that cancels. And I want to know mega becquerels, and that's 1 times 10 to the 6 becquerels. So 1 mega becquerel is the same as 1 times 10 to the 6 becquerels, and that cancels. And so that leaves me mega becquerels. And so if I do all of my calculations, 100 times 3.7 times 10 to the 10 divided by 1 times 10 to the 6, and then divided by that again, and that looks like it's going to leave me with 3.7 megabecquerels. Okay? And so if you got that, you did it right. You got to watch that calculator when you're doing these divisions, because in these divisions right here, you know, you've got to divide by it and then divide by it again, or you've got to multiply them together and write them out. Okay? And that's it for section 9.3 and how we measure and describe absorption and measurement of nuclear radiation.